Hello, this is Dr. Gardner. We're going to be looking at how to calculate different values with respect to chemical formulas. First of all, we'll start looking at how to calculate percent by mass composition of elements present in a formula when we're given the chemical formula. Then we're going to consider cases where we're not given a chemical formula and we want to find out an empirical formula or a compound's actual formula. And we'll go ahead and apply those to problems in today's discussion. So first of all, let's consider the steps we would take in order to find percent by mass composition of elements in a compound when we're given the formula. What you want to do first of all is find the correct compound formula. Either you're given it or you have the name for the compound, you can write the formula from it. With respect to that, you should be able to find the molar mass of the compound. Once you know the molar mass of the compound, you will know how many grams for a 1 mole sample that you have. If that's the case that we're looking at, then we want to find out how many grams of each element in that 1 mole sample. Okay, so if I have element number 1, we can find the number of grams of element 1 with respect to the overall molar mass. Usually if you've set up a table to calculate the overall molar mass of a compound, you already have the mass of each element's contribution to the overall mass. Then we look at every other element in the sample, so I could look at element 2, 3, 4, and so on, and find the grams per mole of that element in the 1 mole sample. And then once we know the grams of every element in the sample, we can divide those element masses by the overall molar mass and multiply by 100 to find a percent composition of each element. So all you have to do is take the mass contribution of each element in that 1 mole sample divided by the mass of the entire sample, if I have 1 mole of it, times 100%. Now we're going to be practicing this calculation, so we'll see how to apply these steps. But always make sure that all of your mass percents of all the elements in the sample should add up to 100%. Okay? So what I can do is, if I know that a compound has so many of every type of element in the formula, I can use that information to find these mass percents. So let's say we have the compound methanol. Methanol has 1 carbon in the formula, 1 carbon atom in the formula, 4 hydrogens if you count all the hydrogens up, and 1 oxygen atom in the formula. So if I was finding the molar mass percent of hydrogen, since there's 4 of them, I would take 4 times the molar mass of hydrogen from the periodic table. So that would give me a value of 1.01 times 4 would give me 4.04. Divide that by the molar mass of the entire compound, if I calculated its entire molar mass in grams per mole, times 100, that would give me the mass percent hydrogen. So for methanol, let's look at this calculation. We have 1 carbon atom in the formula times the molar mass of carbon from the periodic table divided by the molar mass of methanol. The overall molar mass is 32.04, right? Because that's from the 1 carbon, 4 hydrogens, and 1 oxygen. Multiply by 100, that gives me 37.48% by mass carbon. There's 4 hydrogens, so I take 4 times the molar mass of hydrogens mass from the periodic table divided by the molar mass of the entire compound formula times 100. That gives me 12.58% by mass hydrogen. And then I go ahead and there's 1 oxygen, so that's my last element I need to look at in this specific compound formula, times its molar mass of 16 from the periodic table divided by the molar mass of the entire compound of 32.04, multiplied by 100, that gives me a molar mass of 49.94%. If I add up all my mass percents, they should add up to 100%, and they do in this case. That's a double check that I've done all of these steps in my calculation correctly. Now let's see another way we can set up a table to keep track of all these molar masses as we do these types of calculations. Let's consider that we want to find a fairly simple molar mass for, let's say, H2O and the mass percent of every element present in water. So in this case, I need to write the formula for water to start out. So there's 2 hydrogens and 1 oxygen in the formula. So I can set up a table, and the first column in the table will show me the number of each different type of element atom in the formula and how many I have of that element atom in the formula. So for H2O, I have 2 hydrogens in the formula. My second column will show the molar mass of each element that I'm getting from the periodic table. So for hydrogen, I have 1.01 grams from the periodic table for every mole of hydrogen. Multiply that by 2. And I'll get the total number of grams contribution of hydrogen to the overall molar mass of water of 2.02. I do this for every other element, so that's just oxygen in this case. So I have one oxygen atom in water's formula times the molar mass of 16 grams per mole from the periodic table times 1. That gives me 16 overall. So if I have 2.02 grams of hydrogen for a 1 mole sample and 16 grams of oxygen for that 1 mole sample, this adds up to an overall total of 18.02 grams for every mole of the entire formula for every mole of water. Okay. Now, once I know the molar mass and I know the gram contribution of every element in the compound for that mole sample, I can divide by the molar mass. If I divide by the molar mass of the compound of 18.02 and multiply by 100, that'll give me a mass percent of the element. So this is going to give me the mass percent of hydrogen by taking 2.02 grams of hydrogen in this 1 mole sample of water divided by 18.02 grams for every mole of water times 100. That gives me 11.2% by mass hydrogen. I do the same calculation for oxygen, and so I have 16 grams of oxygen for every 1 mole, divided by the molar mass of water of 18.02 times 100, gives me 88.79% by mass oxygen. If I add those up, I should add up to 100% as my double check. So that was a fairly simple calculation. Let's look at a more complex formula. Let's look at the formula for potassium chlorate. There's 1 potassium atom, 1 chlorine atom, and 3 oxygen atoms. Now I'm doing the same types of calculations. I'll take the number of atoms of each type times the molar mass of that element's type of atoms divided by the molar mass of the entire compound times 100. This will give me a mass percent for each element. Okay, so I'm going to show you the overall table that I've set up for this calculation, and then we'll start to develop some of our own tables step by step. So for this table, I went ahead and defined my formula, potassium chlorate, as KClO3. For my number of atoms in each type, I said I had 1 potassium atom, 1 chlorine atom, and 3 oxygen atoms. I looked to the periodic table to find the molar masses for each type of element. So I have 39.10 grams for potassium, 35.45 grams for chlorine, 16 grams per mole for oxygen. My total mass will be the number of atoms in the formula times their molar mass. So for 1 potassium and 1 chlorine, we just have the same mass as the molar mass from the periodic table. For oxygen, there's 3 oxygen atoms though in the formula, so I take 3 times 16 to give me 48 grams per mole with respect to oxygen in the formula. If I add up the gram per mole contribution of all of the elements, that will give me a molar mass of 122.55 grams per mole. If I only had 1 formula unit, these would be in atomic mass units though. If I go ahead and divide the molar mass of the compound into each mass contribution of every element, that gives me a mass fraction. So I'd end up with 0.3191 for the mass fraction of potassium, 0.2893 for the mass fraction of chlorine, and 0.3917 for the mass fraction of oxygen. My mass fractions all add up to 1. That's my parts by mass. So mass fractions should add up to 1 if I've done my calculations correctly. If I multiply my mass fractions by 100, that gives me a mass percent. So I'd get a mass percent of 31.91% potassium by mass, 28.93% chlorine by mass, and 39.17% oxygen by mass. This would add up to 100% overall for my double check. So this is how we could keep a nice neat table that allowed us to calculate the formula mass or molar mass, and how we could find out mass fractions of percent by mass by keeping very careful track of our data. So it's important you write down your steps in these calculations to keep track of everything carefully, and then double check that parts by mass, your mass fractions add up to 1, your mass percents add up to 100%. Now let's find the mass percent of every element in calcium nitrate. So here I'm given the name of a compound, so I'm going to have to be able to write the formula from that name. Now the cation in this formula is calcium. It's an alkaline earth metal in group 2, so it's a 2+ charge. Now nitrate, since there's an ATE at the ending, if I see ATEs or ITEs, that indicates that I have an oxo anion. So here we have nitrate, so we're going to have the formula NO3- that you should have learned before when we were covering oxo anions. It's one of the first ones that you were required to memorize. Now since nitrate's formula has just a -1 charge, I'm going to need 2 nitrates to balance the charge on the calcium's 2+ charge. So I need 2 nitrates. So when I write the formula for calcium nitrate, I'll show calcium, and inside brackets, inside my parentheses here, I'm going to have NO3 for nitrate, and I have 2 of them, so I put outside of those parentheses a subscript 2. That indicates 2 nitrate anions. that means I have 2 nitrogens in the formula and 6 oxygens in the formula. So you can always take this subscript 2 times the subscript of a 3 or a subscript of a 1, which isn't shown here for nitrogen. That gives me the number of nitrogens that's 2 and the number of oxygens is 6. So I have 1 calcium atom, 2 nitrogens, and 6 oxygens. So when I set up my table, I'm going to start with the number of each different type of element atom in the formula. I have 1 calcium atom in the formula, so I go to the periodic table and find the molar mass of calcium as 40.08. The total contribution, now this should be calcium nitrate, not H2O here, but my total contribution is 40.08 grams per mole of calcium, since there's only 1 calcium atom. I have 2 nitrogen atoms in the formula, so I look at the molar mass of nitrogen as 14.01, multiply that by 2 because there's 2 nitrogens in the formula. That gives me 28.02 grams per mole of calcium nitrate. And for oxygen, since there's 6 oxygens in the formula, remember there's 2 nitrates, so 6 oxygens total. I look at the molar mass of oxygen as 16 times 6, gives me 96 grams of oxygen for every 1 mole of calcium nitrate. So if I add up my grams of calcium in this mole sample, my grams of nitrogen in this 1 mole sample, and my grams of oxygen in this 1 mole sample, that gives me a total of 164.10 grams of calcium nitrate for every 1 mole of calcium nitrate. Now, if I divide my molar mass of my compound into each gram total of every element times 100, that would give me a mass percent. So I take 40.08 grams of calcium in this 1 mole sample divided by 164.10 grams for an entire mole of this compound times 100. That gives me a mass percent of 24.42% by mass calcium. I go ahead and divide that molar mass into each one of my gram totals for each element. So I take 28.02 grams of nitrogen divided by 164.1 times 100. That gives me 17.0% by mass nitrogen. If I take 96 grams of oxygen divided by my molar mass of 164.10 times 100, that gives me a mass percent of 58.50% oxygen. If I add up all my mass percents, they should add up to 100%. Here we're very close, 99.99%. I probably had a slight rounding error because I did round at a few steps here. But that's close enough to 100 that we should feel fairly comfortable with this calculation. So there's my mass percent composition of every element in this compound formula. Now, sometimes we won't be given a compound formula, and we'd like to find out what the actual formula for this substance would be. So we're going to have to consider when we have empirical formulas. When I have empirical formulas, these are going to be the formula for a compound when we're looking at the subscripts for the number of atoms of each element in the compound formula as being the lowest whole number set of integers for the ratio of atoms in the compound. Now this may or may not be the same as the actual formula for the compound. For ionic compounds, the empirical formula, the simplest ratio of the atoms, is usually the same as the actual formula for the ionic compound, because we have the simplest ratio of the ions in most cases. However, if we have a molecular compound, many molecular compounds have several times the empirical formula's numbers of atoms. So let's look at a few examples of this. Let's say we consider benzene. Now, benzene is a cyclic compound with 6 carbons in a ring structure and 6 hydrogens. There's actually alternating double bonds, covalent bonds between the carbons, which we'll talk more about when we look at Lewis structures in the course. Now, benzene has 6 carbons and 6 hydrogens. However, the empirical formula would simplify to the simplest whole number ratio of the number of atoms. So that would be a 1-to-1 ratio. So the empirical formula is C1H1, or just CH. The molecular formula is actually 6 times that. Now, one way I could figure out the difference between these two is if I actually analyzed the compound by different experimental techniques. For example, I could use mass spectrometry that we talked about when we looked at determining isotope masses. If we go ahead and find the molar mass of the actual compound, it would have a mass that had 6 carbons and 6 hydrogens, whereas the empirical formula's molar mass would just be 12.01 for the carbon and 1.01 for the hydrogen. It would be 13.02 grams per mole. Since that would be 6 times that molar mass for the actual compound, we know we'd have to take the empirical formula whole number integers and multiply by 6. So 1 and 1 would go to 6 and 6. Now let's see why it's important that we be able to determine both empirical formulas and molecular formulas in this chapter. Some compounds will have different molecular formulas. Like acetylene has 2 carbons and 2 hydrogens. But I want you to notice if we simplify that ratio to the simplest whole number ratio, that's still the same empirical formula. So some molecular compounds will have the same empirical formula but different molecular formulas. So we're going to have to determine both of these in this discussion today. Let's consider a case where we have glucose. Now glucose will have a different empirical formula than benzene and acetylene, but let's take a look at it. The actual molecular formula for glucose, which is blood sugar, is C6H12O6. There's 6 carbons, 12 hydrogens, and 6 oxygens. If I have my simplest whole number ratio, I can divide each of these subscripts by 6, so I get 1 carbon, 2 hydrogens, and 1 oxygen. So the empirical formula is CH2O, or C1H2O1. Right? So that's my simplest ratio, that's my empirical formula. A lot of experimental techniques will help us find these empirical formulas, and then we'll have to analyze the compound in greater detail to find a molecular mass and then find the actual molecular formula. Now let's consider carbon dioxide. Carbon dioxide's formula has 1 carbon and 2 oxygens, so it's CO2. The simplest ratio of the elements for this case is still the empirical formula. So there will be a few cases with simple compounds where the empirical formula is the same as the molecular formula. But there's many cases where they are not the same. Okay, now the first step in order to understand how to find empirical and molecular formulas is looking at how to take experimental data and find an empirical formula from that information. So let's consider something that we already know the formula of, but let's pretend we don't know the formula of water. We already know it's H2O, but let's say we're given some experimental information and we want to find the actual formula, the empirical formula for H2O. So somebody analyzes a substance that we think is water, and they find the mass percent of hydrogen is 11.21% by mass hydrogen. The mass percent of oxygen is 88.79 mass percent. Those add up to 100, so that tells me that's all of the elements present in the sample based on that data. Now, in order to calculate the empirical formula for this compound, I'm going to go ahead and say the empirical formula is going to have 2 unknown values, X and Y. I don't know how many hydrogen atoms in the formula, I don't know how many oxygen atoms are in the formula, but I know it should be a simple whole number ratio. Now, when you're given mass percents, it's very useful to make an assumption. No matter your sample size, no matter what size the sample is, assume you have a 100-gram sample. It doesn't matter if your actual sample size is 100 grams or if it's some other mass quantity. If you pretend you have a 100-gram sample to do the calculation, that's very useful because I'm dealing with percents out of 100, right? So if I have a 100-gram sample, I must have 11.21 grams of hydrogen and 88.79 grams of oxygen. So we assume we have a 100-gram sample. I have 11.21 grams of hydrogen in that case, based on my mass percent value. If I look up the molar mass for hydrogen of 1.01 grams of hydrogen, divide by that for every 1 mole of hydrogen, this will give me how many moles in this 100-gram sample I have of hydrogen. Now, once I get to these mole quantities, they should relate to my integer whole number ratios. I can't take gram quantities directly, so I must convert from grams to moles. So I get 11.09 moles of hydrogen in this 100-gram sample. I'm going to do the same calculation for oxygen. So I have 88.79 grams of oxygen. Divide by the molar mass of oxygen of 16 from the periodic table. That gives me 5.549 moles of oxygen. Now this isn't simple whole number ratios, is it? So I need to go ahead and take one more step and try to simplify this ratio. So I look at the mole quantities of all the elements in my sample and divide by the smallest value into each one of these. So the smallest value of all my elements is the 5.549 moles of oxygen. I want to take that value and divide that into both. The reason I'm doing that is I'm forcing this ratio to simplify to 1 mole of oxygen, and then I'm seeing how many moles of hydrogen there would be in comparison. So I take 5.549, the smallest of my number of mole quantities, divide that into both. That gives me 1.999 moles of hydrogen. That is very close to 2. If we're within less than 0.1 number of moles, we can usually round to a whole number. So I have 1.999 moles of hydrogen and I have 1 mole of oxygen. So I have 2 hydrogens for every 1 oxygen in my formula. So my X is 2 and my Y is 1. So that helps me solve for my empirical formula, which for water is the same as the molecular formula, right? H2O1 or H2O. So we just solved for an empirical formula for a compound from only being given mass percents. Okay, so we're going to use the same technique for some other compounds. So let's try a compound you don't know the actual formula for. We don't know the empirical formula for it. So let's say we are analyzing a compound that has just carbon and hydrogen as the elements in its composition. So my carbon is going to be 92.3% by mass, and my hydrogen is going to be 7.7% by mass. So I'm trying to find an empirical formula when I want to know my x and my y. How many carbon atoms in the formula for how many hydrogen atoms in the formula. Should be nice whole numbers though, and the simplest ratio of the two to be an empirical formula. Now, if I have mass percents, an assumption that will really help you out, and it doesn't matter your actual sample size, but assume you have a 100-gram sample. Okay, if I have a 100-gram sample, I would have 92.3 grams of carbon. If I divide by the molar mass of carbon of 12.01 grams of carbon for every 1 mole, that tells me this 100-gram sample has 7.68 moles of carbon content. I have 7.7% by mass hydrogen, so if that's a 100-gram sample, I would have 7.7 grams of hydrogen. I divide by the molar mass of hydrogen, which I get from the periodic table of 1.01 grams of hydrogen for every 1 mole of hydrogen. That gives me a value of 7.6 moles of hydrogen. So these values are close to the same, so you might think it's close to a 1-to-1 ratio. But let's go ahead and take the smallest of the two values anyway, 7.6, divided into both. To simplify my ratio, that tells me I have 1.01 moles of carbon and 1.0 moles of hydrogen. Remember when I said that if you're less than 0.1 away from a whole number, you can round? It's probably some experimental error here with the data that was collected, or maybe a rounding error. As we look at that, I'm going to find then for every 1 carbon atom, there'd be 1 hydrogen atom. Okay? So my empirical formula would have an x of 1 and a y of 1. So it's C1H1 or just CH. So this matched our empirical formulas we saw earlier for benzene and acetylene, and it can also represent some other compounds that have a 1-to-1 ratio of carbon to hydrogen. So I don't know what the actual formula is here necessarily. In some cases the empirical formula will match the molecular formula, but in many cases they will not. So I need a little more information in order to find out the actual formula, to see if it matches the empirical formula. So with that information, let's find out the molar mass of our empirical formula for CH. So my empirical formula here says there's 1 carbon atom in the empirical formula. I take 1 times 12.01. There's 1 hydrogen atom in the formula, so I take 1 times 1.01. I add those up, I get a molar mass for CH, my empirical formula here, of 13.02 grams per mole. If the actual molecular compound molar mass is the same value, then the molecular formula and the empirical formula would be identical. If it's several times this, I may have a more complex molecular formula. So let's say we give this sample to a technician to run a mass spectrum. My mass spectrum will allow me to find the molar mass of the compound based on the individual molecular units. So the mass spectrometry data shows I have a molar mass of 78 grams per mole. Now immediately I say to myself, 78 grams per mole is not identical to 13.2 grams per mole. So my empirical formula is probably simplified from an actual molecular formula. My molecular formula should be several times my 1-to-1 ratio. So in order to find how many times the empirical formula would have to be applied to find the molecular formula, we take the actual formula mass. That's from the mass spectrometry, or from some experimental data that we were given, of 78 grams per mole. Divide that by the formula mass, or the molar mass, from the empirical formula that we calculated. So I take 78 grams per mole for the actual formula mass, divide it by the empirical formula mass that we calculated, and I find that the actual mass is 6 times my empirical formula mass. That means I need to multiply my subscript 1s here for carbon and hydrogen by 6. So I'm going to have to multiply those by 6 to get the actual formula for the compound. So the actual formula is C6H6. This looks like it may be benzene. That matches our molecular formula for benzene. So just remember, if you take the actual formula mass divided by the empirical formula mass, you can determine how many times to multiply the number of atoms in the empirical formula to get the actual formula. In this case, it's a molecular formula because we're looking at a molecular compound. Okay. Let's go ahead and consider a situation where we have more than 2 elements present in my sample. So let's consider if I have some mass percent information for a compound that contains 3 elements. So let's say we have a compound that has zinc, nitrogen, and oxygen, but we only have mass percent data for 2 of the 3 elements. So I'm told I have 34.5% by mass zinc, 14.8% by mass nitrogen, and the rest of the mass must come from oxygen, but I'm not given an actual mass percent. Now I know if I have all the elements here with these three elements that their mass percent should add up to 100. So I can find the mass percent of oxygen by difference. So if I take 100% and subtract the percent of zinc and nitrogen, that would give me the difference in mass that must be from oxygen, so my mass percent of oxygen. So I take 100, subtract 34.5% by mass zinc, subtract 14.8% by mass nitrogen. I end up with 50.7% by mass oxygen. All of my mass percent should add up to 100. So now that I have all of my mass percents, we can solve for our empirical formula. Now I have three variables to solve for here. So let's say it's x, y, and z. I would like to know how many zinc atoms in the formula, and how many nitrogens, and how many oxygens. So I'd like to nice whole number integer values here for each of those. And so if I start to look at this sample, I can assume a 100-gram sample. The reason why, remember, is that my mass percents will play nicely with a 100-gram sample to find gram quantities that are the same value as my mass percents. It doesn't really matter if the actual sample is 100 grams here. This just simplifies the calculation for us. So if I have a 100-gram sample, I must have 34.5 grams of zinc because it was 34.5% by mass. Divide by the molar mass of zinc of 65.39 grams of zinc for every 1 mole. That gives me 0.528 moles of zinc present in this 100-gram sample. I do the same calculation for the other elements. So I have 14.8 grams of nitrogen in this 100-gram sample because it's 14.8% by mass, divided by the molar mass of nitrogen of 14.01 grams. I'm getting this from the periodic table, you recall. This gives me 1.06 moles of nitrogen. And then if I do the same calculation, we'll come back to this in a second. For oxygen, I have 50.7 grams of oxygen. Divide by the molar mass of 16 grams of oxygen for every 1 mole of oxygen. That gives me 3.17 moles of oxygen. So I know my mole quantities of every element. They aren't simple whole numbers. So I look at the smallest of each of these number of moles. That's the zinc. So I only have about half a mole of zinc, whereas I have about a full mole of nitrogen and about 3 moles of oxygen. So I'm going to take 0.528 moles, divide that into each one of these. That simplifies my molar ratio of zinc to 1. And then I get 2.01 moles of nitrogen. I divide that into the oxygen, I get 6.00 moles of oxygen. So they get me very close to whole numbers. If I'm less than 0.1 away from a whole number, I can usually round. So that tells me I have about 1 zinc atom in the formula for every 2 nitrogen atoms and about 6 oxygen atoms. So my x, y, and z is going to be 1, 2, and 6. So my empirical formula, I can write it as Zn1 N2O6. Now, I want you to think about what you think this compound may be. My clever students might recognize that this would also match the formula for zinc nitrate, because there would be 1 zinc atom, 2 nitrogen atoms, and 6 oxygen atoms, but present as 2 nitrates. So if you recognize that, you should pat yourself on the back for quickly recognizing a common type of ionic compound you may have seen before. Okay, so this is how you deal with samples that have 3 elements. If you had any more than 3, you just continue on with this calculation for every element in your sample. Let's consider a situation where we have aluminum and oxygen. So we have a compound with just 2 elements. I have a 53% for my mass of aluminum and 47% for my mass percent of oxygen. My empirical formula, I'd like to solve for how many aluminums and how many oxygens, so I'm solving for x and y. Since I have mass percents, assume you have a 100-gram sample. So we have 53 grams of aluminum divided by the molar mass of aluminum that I'm getting from the periodic table of 26.98 grams of aluminum for every 1 mole. That gives me about 2 moles of aluminum. If I take the 47 grams of oxygen, divide by the molar mass of 16 grams per mole of oxygen, we get 2.9 moles of oxygen. Now, based on what we've learned, we could divide these by this lowest number of moles. That would be 2. If I do that, I end up with 1 mole of aluminum for every 1.45 moles of oxygen. Now, in this case, we actually kind of took a step back by dividing by the lowest number of moles. We have roughly 1.5 moles of oxygen. We're within less than 0.1 away from that, so that's pretty reasonable to look at that. I need to have whole numbers here. So if I multiply by 2, that gets me close to my whole numbers. I know I'm going back to 2 to 2.9, but my 2.9 is close enough in this case that we could round to a whole number. So I get 2 aluminum atoms for every 3 oxygen atoms. Now that 0.9 is really borderline. In some cases, we might want to multiply by 10. In this case, a 2 to 3 ratio, though, makes sense because I would end up with aluminum oxide, where I have 2 aluminum cations and 3 oxide anions to balance charge. Okay, so there's a case where we don't get nice whole numbers. If we don't get nice whole numbers, we need to multiply by a number that will get us close to a whole number, within less than 0.1 usually. Then we can round to that whole number. Let's consider a case where we have a molar mass for the actual compound given, and maybe we're not given mass percents. So here we're told that we have a compound that contains phosphorus and oxygen that has a molar mass of 284 grams per mole, and we're told that we have a sample that contains 10.48 grams of phosphorus and 13.52 grams of oxygen. Now I certainly could add these up to get my overall sample size and calculate mass percents, but that's not what I have to do in this case. If I'm given grams of each element in my sample rather than mass percents, then don't assume a 100 gram sample. We don't have to do that necessarily. If I'm given gram quantities, I can still convert these gram quantities to moles and find my simplest molar ratio. Okay, so I'm trying to find the empirical formula for this compound that has phosphorus and oxygen. So I want to know X and Y. In this case, since we weren't given mass percents, do not assume a 100 gram sample. If mass percents were given, then if they were not given here as mass percents, then that's probably not very useful. It's mostly useful when you're given mass percents of all the elements. So if I have 10.48 grams of phosphorus, there's no reason why I can't convert that directly to moles and get a molar ratio without having to work with mass percents. So I don't have to assume a 100 gram sample here. So I look up the molar mass of phosphorus. It's 30.97 grams on the periodic table for every 1 mole of phosphorus. Divide that into the number of grams in the actual sample of phosphorus. That gives me 0.3384 moles of phosphorus. I do the same calculation for oxygen. I have 13.52 grams of oxygen divided by the molar mass of oxygen of 16 grams for every 1 mole of oxygen. That will give me a value of 0.8450 moles of oxygen. I look at whichever one of these is smallest because this isn't a nice whole number ratio. Whichever is the smallest number of moles, if I divide that into both, that'll force one of them to a value of 1 for my ratio. So I divide 0.3384 into both values. That forces my moles of phosphorus in this ratio to 1 and my moles of oxygen to 2.497. I don't have nice whole numbers here, but this value for the moles of oxygen is close to 2.5. If I get close to 2.5, we can multiply both of these by 2, and that would give me 2 moles of phosphorus for every 5 moles of oxygen. It gives me a nice whole number that I can work with. So that would be my empirical formula I'd predict. Empirical formula would be P2O5. Now, I can find the molar mass from the empirical formula by taking 2 phosphorus atoms in the formula times their molar mass at 30.97. Gives me 61.94. I have 5 oxygens times 16 for the molar mass for oxygen. That gives me 80. If I add those up, that tells me a 1 mole sample would weigh 141.9 grams per mole. Notice that does not match the actual formula mass of 284 that we were told. So if I take the actual formula mass of 284, divide by the molar mass of the empirical formula of 141.9, I get 2. That tells me how many times I must multiply by my subscripts here, 2 and 5, to get the actual molecular formula. So I need to take 2 times 2 and 5 times 2. That gives me an actual molecular formula that is P4O10. So I get tetraphosphorus decaoxide. Whereas I had originally for the empirical formula, it looked like I might have had diphosphorus pentoxide. Okay, so we had to have twice the number of phosphorus atoms and twice the number of oxygen atoms to get my actual molecular formula in this case. Okay, so far we've looked at how to do quite a few calculations involving finding mass percents of elements and compounds, as well as how to find empirical formulas. And if I'm given an actual formula mass, I can find my actual formula. Okay, so I'd like you to practice these techniques. So as a group, I'm going to give you an open-ended question that I have not given you the answer to. I'd like you to work in groups and try to find your answer and then work with the local instructor that is there on site to help you if you get stuck. So here's the question I'd like you to all work on. We're analyzing a compound and we're told that it's 50% by mass carbon and 50% by mass oxygen. And then we run a mass spectrum of this sample and find that its molar mass is 288.12 grams per mole. I'd like you from this information to find the molecular formula of this compound. And while you're doing that, you may want to find the empirical formula first before you find the molecular formula, or see if they're identical. So try to solve this question. It's going to be one of the following answers. If you get stumped, like I said, please have your instructor on site help you with this. Okay, thank you and good luck.